Okay, this is Mrs. Query's components of a vector. We have to learn about components of a vector in order to add vectors algebraically. Okay, they can be added or subtracted algebraically, but we have to break them down into their components. We're going to have two components of vectors in our class because we're working in two dimensions. We're going to have an x component and a y component. In physics, pre-cal and calculus, you might be doing x, y, and z. I know for a fact if you're going into certain types of majors in college, you'll be in 3 dimensions, but we are in 2. So we will only have components in the x and the y. Okay, so how do we do that? How do we break a vector in to its components? If we draw our vector A, here's our vector A, we can look and see that that vector, which has some magnitude and direction relative to, let's say, the x-axis, I can then take a look at vector A and see that it has a reflection on the x-axis. That is its component in the x direction. In the same manner, I can see that it has a reflection in the y, on the y-axis. That is its component in the y direction. And so, for example, I can take and draw that component, a sub x, so that's the x component of that vector. I can add to it its component in the y direction, and I will find that that resultant vector is A originally. So the vector A is the addition of its x and y components added vectorially, which is this tip to tail orientation, and we will find that we have the same angle here. Okay, so okay, so every vector has a component in the x and y direction. It can be 0, by the way, and we'll have a couple that look like that in just a minute. So we can see now the projection of A along the x-axis is A sub x, or its x component. The projection along the y-axis is its y component. Okay, now here's a very important statement. It can be either positive or negative number with units. Now, in pre-cal, you guys go by standard position. You're always measuring the angle from standard position, which is the positive x-axis. So if you're in the second, third, or fourth quadrant, you're going to be between 90 and 180, or 180 and 270, or 270 and 360 degrees. When you use that standard position, when you take the cosine or sine of an angle that's at standard position, the negative will be displayed automatically on your calculator. We're not going to use standard position. So we're going to have to make decisions about whether or not the component of a vector has a negative value or a positive value. In the case that I just showed you right here, these have both the positive values. How do I know that? Because they are pointing to the right on the x and they're pointing up on the y. And so those are considered positive, assuming that we've defined to the right as positive and up as positive, okay? We can have weird scenarios where that isn't the case. So you have to pay attention to that. But again, that's not always, that's not normal. Okay, so now let's draw let's call vector B exactly as vector A, but just in a different direction. And then let's draw its components. So its reflection on the x-axis, its reflection on the y-axis. And notice that this B vector has a negative x component. So I have to pay attention to which axis the reflection is on. Is it on the positive or negative axis? Because we're not using standard position. We're using just this angle right here would be some angle, we'll call it theta, above the negative x-axis, or north of west. Okay, that's the subtle difference between pre-cal standard position measurements and what we do in physics. Okay, all right. So notice that the components for two sides of a right triangle with a hypotenuse of magnitude A, that the components form. That's actually what it was supposed to be, but what it should say. It should say form. This is a right triangle. This is a right triangle. Okay, so now that I have a right triangle, if I know the components of a vector, I can use trigonometric functions to find everything else I need to know. I can find the hypotenuse, which is the resultant. I can find the angle, which will give me direction. Or if I'm given the resultant vector and asked to break it down into its components, as long as I have the direction, I can determine that as well. So I always have to write SOHCAHTOA on my sheet when I'm doing SOHCAHTOA problems. I always get them confused. So what does that mean? That means the sine of some angle theta is equal to the opposite over the hypotenuse. The cosine of some angle theta is equal to its adjacent value over the hypotenuse. The tangent of some angle theta is equal to its opposite side divided by its adjacent side. And so here are these are the SOHCAHTOA values for the resultant or the vectors that I have shown here. And then if that has to do with the angles, and then we have this wonderful Pythagorean theorem, which tells us that the hypotenuse squared is equal to the x component squared plus the y component squared. Okay, so a little bit of trig review, which we've already done. All right, now examples of how we're going to algebraically here's an example of how we're going to solve a problem using algebra. Okay, I have a hiker. He begins his trip. He first walks 25 kilometers, 45 degrees south of east from her base camp. On the second day, she walks 40 kilometers in a direction of 60 degrees north of east, at which point she discovers a forest ranger's tower. Determine the hiker's displacement from the base camp to the end trip. Now, let's just look at this graphically. So here's where she starts at camp. She walks at an angle of 45 degrees south of east. So here's my 45 degrees south of east. And I've gone, that value A is equal to, so she goes, A is equal to 25 kilometers at 45 degrees south of east. Okay, and then she walks. So how would I have to add B to it, tip to tail. And B is equal to 40 kilometers at 60 degrees north of east. So notice that when they drew that, here's east, and they went 60 degrees north of east. So I started at east and I went north, okay? All right. I gotta pause because I'm gonna lose power. All right, I'm back. I got power. Okay, so, all right, there's my two vectors, and then this is the question. They want to know what are the components of the displacement vectors from on day 1 and day 2. So we are going to find the components of vector A and vector B. So let's take vector A first. So I have vector A, and that is equal to 25 kilometers. And I have some angle, 45 degrees south of east, and that's where people struggle, knowing where to draw that angle. I have a reflection of that vector on the x-axis. That is its component in the x direction. Notice it's pointing towards the positive. I have a reflection of that vector, not very well drawn to scale, I know, of that vector in the y, of that vector, which is vector A, in the y direction. Notice that vector will be negative because it's pointing downward, and I need to find them. And how do I find them? Well, I know the hypotenuse, and I'm trying to find in the x direction that is adjacent. So if I go up to SOHCAHTOA, I see that I need a cosine of the angle, cosine of theta, which is 45 degrees, is equal to its adjacent, which is what I'm looking for, over the hypotenuse, which we know. Okay, so I then find that A sub x is equal to the hypotenuse times the cosine of the theta, which is 25 times cosine of 45 degrees. Now I need to do the same thing for y, and y, or the component of that vector in the y direction, that is located opposite of the angle that we have. So, and I have the hypotenuse, and so I'm going to use sine. So I know that sine of the theta, which I have is 45 degrees, is equal to the y component of that vector divided by the hypotenuse, and I will find that its y component is equal to the hypotenuse times sine of theta, which will be 25 times sine of 45 degrees. Now, sine of 45, cosine of 45, the same thing. Both of those values will come out to 17.7 kilometers. If you plug that into your calculator, you will find them to be exactly 17.7 kilometers. And if you left it as that, you're going to get the problem wrong. And the reason why you're going to get the problem wrong is because what direction is the y component pointing? It is negative, therefore that is a negative 17.7 kilometers. So in pre-cal, you would have used standard position, which would measured it all the way back to the x-axis, positive x-axis, and that would have taken care of the sine. So please pay attention to that. It is a common error, okay? Now, we got to do the same for b. So for b, I have this vector b, and I have a projection on the x-axis. I have a projection on the y-axis. So here's where graphically actually makes sense. We have to know how to draw these graphically because it helps us it helps us determine, you know, positive, negatives. I mean, so there is value. I don't want to make it sound like the graphically addition is of no value. It is. Okay, so I know that this is 60 degrees, and then I can solve for by, which is equal to the hypotenuse times sine of the angle, which is 60 degrees, and I find that to be 34.6 kilometers. Ask yourself, is it positive or negative? It is pointing upwards, therefore it's positive. I know in the x direction, it's the hypotenuse times cosine of the angle, and that will be equal to 20 kilometers. I ask myself, is it positive or negative? It's pointing toward the right. We're assuming that is positive, therefore it's positive. Now, I have constructed a data table for this problem. And I like to keep track of my data in a table in all cases personally. So I want to know a values in the x at 17.7. What is it in the y? Negative 17.7. And then for b in the x is 20. Whoops, I want green. And 34.6. Okay, data tables are huge. Organize your work. Will solve many problems. You won't make as many mistakes. Okay, so let's go back to our question. Did we find the components of the two vectors? And we did. Here are our answers. These are our two answers for A. Do I have to give a direction? The negative gives me the direction. I'm only in the X or Y direction. I don't have to give you some angle, okay? Because I know that if I'm giving you a component in the X direction and it's positive, it's to the right on the X axis, okay? I hope that makes sense. All right, determine B, the components of the hiker's total displacement. So we want to know the components of that R vector that we're trying to find, okay? Well, how do I do that? I come to now I can actually add these values, add up all the X's, add up all the Y's, okay? And now I don't have to show it on a graph, I can actually just add them. And what are they? They equal, this just becomes 37.7 kilometers, and this becomes 16.9 kilometers. So this is my component of R in the X direction, and it's positive, so I've got to draw that to the right. And this is my component of the resultant vector in the Y direction, and it's positive, so it's also drawn upwards. So that is my answer to B. Part C wants to know the magnitude and direction of R. Well, if I know the components, remember that R is equal to just the addition of their components in the X and Y direction. So this is where being able to draw it helps. So draw Rx in the correct direction, Ry. So this is 16.9 kilometers. This is 37.7 kilometers. And then draw the resultant vector. Start at the origin, go to the final location. Now I know my angle. That angle is the angle above the positive x-axis, or the angle north of east. Okay, now how do I find R? Well, I have two sides of a right triangle. I use Pythagorean theorem, so I know that R squared is equal to Rx squared plus Ry squared, and then I solve for R. So R is going to be equal to, what did I find? 41.3 is what I got. Kilometers. I'm not done. They asked for the magnitude and direction of the displacement. I have found the magnitude. I now need to find theta. So I would use maybe the tangent of theta is equal to the opposite over adjacent. What is the opposite? That is the R, the Y component of R divided by the adjacent, which is the X component of R, and then I will take the inverse tangent of both sides and solve for theta, and I get theta is equal to 24.15 degrees. Now, how do I write my answer? I write my answer in this way. The answer is 41.3 kilometers at 24 point, let's call it 0.2 degrees north of east. That's one way to write it. 41.3 kilometers at 24.2 degrees above the positive x. Let's assume we're using the x-axis. What about the complement of 24.2? Can't do that in my head. $65.8. I could say 41.3 kilometers at 65.8 degrees. So that would be east of north. All three of those are accurate, okay? Okay, nope, I got one more thing to talk about and then I'm done for today. Now, flipping physics, I have put links. All the links for every single flipping physics video now is located in your Google Classroom under class resources. They are amazing little tools. He will go through a visually complicated vector addition problem using component vectors. So if you're struggling with this and you want him to watch him actually work this problem out step by step, where he shows you graphically and algebraically on how to do this problem, he takes a car that goes 60 meters west. So here's 60 meters west, then turns and goes north. So here's the northern portion of it, then turns and goes meanderly at 40. This is not a speed, this is a displacement, sorry. I could have speed, but then we go 40 centimeters southwest, didn't give an angle, so we have to assume 45 degrees. What was her total displacement? So I'll say, what is her total displacement? Well, I would start from the origin, draw it to the final location, and then if I had it to scale, I could measure its magnitude, determine its angle using a protractor, or I can add all of these vector quantities up algebraically after having split the vectors into their x and y component, which he does. So A is in yellow, and he has broken A up. Notice A has 0 in the y direction. Well, originally he only went to the, let's see, what is that? west. And so that is, it has nothing in the y direction, okay? And then B, which was, I had blue, has only a direction north. So it only has a positive y direction. C, however, the car's displacement had both an x and y displacement. And notice that both of those displacements were negative, okay? Because it had a reflection going downward on the negative x-axis, or pointing down on the x-axis, and also, I'm sorry, pointing down on the y-axis and pointing to the left on the x-axis. And also notice the values are the same because it was 45 degrees, and sine of 45 and cosine of 45 are the same. So when you use SOHCAHTOA, you found the same thing, okay? He adds all of them up. He adds all of them up algebraically, and once he knows the component values for the resultant vector, he draws the actual components of that and solves this right triangle to determine the magnitude of the hypotenuse, which is the displacement vector, and this angle, which will then tell me how many degrees north of west he's located, or above the negative x-axis. So, struggling with that, go back, find this in my links under course resources, and watch him go step by step through that problem. I suggest you try it yourself. You don't even need the graphs if you started to get feeling comfortable with that. Create a data table, your x components, your y components, add them up, find your resultant vectors and your angles using trig, okay? That is what I got for you today. We're going to go over some vector worksheet in our synchronous learning tomorrow. Have a wonderful day.